welcome to our presentation for the lift coursework. My name is Jake Phillips and I worked with Oliver Robson, Doruk Aksu and Thomas Wilkin-Jones to create this project. My primary contribution to this project was the documentation, so I created the main coursework PDF file, which contains the objectives that we were trying to do, the sort of background of this project, the design process and the thought process behind the technical implementation. As well as doing that, I created this video you're watching right now. As well as those things, I did contribute to the code as well. I was the one who suggested using a JSON file instead of a text file for the inputs, mainly because it's a lot easier to work with JSON files in Python compared to text files. And they're a lot easier to work with for the user as well. So I created the loader.py file, which contains the load file function. And what that does is you give it the path for a JSON file and it will extract the capacity, the floor count, and where everyone is in the lift system. It will then return that to you as a list of passenger objects. As well as that, I created the bulk testmaker.py file, which contains functions to make hundreds and hundreds of test files all in one go. This is primarily used for comparing the performance of the different algorithms over a range of values. So what we do is we vary the capacity from 1 to 50, the floor count from 2 to 100, and the passenger count from 10 to 1000. These files are generated a total of 10 times, and then later on in the program, an average is taken of these 10 files so that we get a more accurate representation. What then happens in the main.py file is all that data is collected. So we collect how long the algorithms took to run in real time, the time it takes for the algorithms to run in fake time. This gives a representation of how long these algorithms would take to run if this was implemented in a real lift. The average journey for a passenger from their start floor to their end floor, and the maximum journey that was processed. We then take all of that information and put it on a graph using matplotlib. With these graphs, you can visually see what effect varying these parameters does to the functions, and which function performs the best. As well as that, I created the main user interface, so the user has options to run a test file, generate a test file, or run lots of test files at once and generate these graphs.
Hello, I'm Ollie Robson, and this is my part for the coursework. So during the creation of the coursework, I was the one who made most of the boilerplate code, with the first things that I created were being the passenger and lift classes, specifically the initialization and the specifics of the open doors algorithm. The passenger class I created was the way that we were going to use to store the information for each passenger. And the lift class was obviously the class that has the look, scan, and mylift algorithm, which were created by other people. However, despite the algorithms being made by other people, when it came to testing, I was the one who mainly was the debugger, having to go through and work out the infinite loops and work out how to shorten them. Additionally, I was the one who came up with the initial test generator. We then moved on to a different test generator named bulk test generator.py, I believe. But my initial one has a setting for random, which is a random case, and the best case scenario for the layout of passengers on each floor. So in this best case scenario, you'd have passengers on floor 1 wanting to go to floor 2 going to floor 3, on and on, but there'd be enough passengers in floor 1 wanting to go floor 2 that the entire lift would be full on floor 1. Then it would completely empty on floor 2 and then be completely filled again, and then carry on going up, moving the maximum number of passengers in each sort of floor moving up, and that will result in a sort of parallelism where you get multiple people going on and off all at once, and then it will create a chain of passengers going up and down, meaning we have the minimum number of lift moves for any sort of case with a fixed number of passengers per floor. And finally, for the coursework, I was the main author of all the doc strings, just to ensure that the documentation was kept up to some level of scratch. I've attempted to provide explicit typing for all the inputs and outputs of the functions, except for those functions where specific typing is detrimental. For example, in the heap sort algorithm, I did do the typing to be a list, not specifically the list of passengers, because it can work with any 2 passengers. That is my entire contribution. It's the boilerplate code, the debugging of any errors that came up, and then the documentation of the code. Yep.
Hello, my name is Thomas Wilkin-Jones, and my responsibility in this project was to develop both the scan and look algorithms for our lift system. Both are fairly similar, so they had a lot in common when I was implementing them, but the key difference was how they changed direction. The scan algorithm will only invert when it reaches the top of the lift shaft, so I only needed to check the current floor of the lift against these values, the top and bottom, but the look algorithm will invert when it has no more requests to serve in the direction it's currently travelling in. I therefore designed this algorithm to check both the requests of the lift's current occupants and those who are waiting to get in the lift, to make sure it only inverted when it had no more to serve. I also created a function to check the direction that each person waiting wished to travel in, and this meant that I could make sure the lift would only pick up passengers who wanted to go in the same direction the lift was currently travelling. This in turn helped to increase the efficiency of the lift, as people wouldn't take up more of the lift space when they didn't need to.
Since both algorithms shared a lot of code owing to their similar implementations, they bear similar performance. The main time saving in the look algorithm comes from turning around before the top or bottom. So overall, graphing the performance while varying each parameter creates similar shaped graphs. For my first test, I increased the total number of floors and the total number of people in the system, while maintaining a constant ratio of 10 people per floor, and I kept the lift capacity constant. The look algorithm was roughly 11% faster than the scan algorithm, no matter how many floors there were. My second test, I kept the capacity of the lift constant as well as the number of floors, and increased the total number of people in the system. This led to, again, a fairly consistent time saving of 6%, comparing the look algorithm and the scan algorithm. However, varying the lift capacity while maintaining a constant number of floors and people led to a less consistent time saving with the look algorithm. With a capacity of 2, it presented a massive saving of 15%, but with a capacity of 12, it was only 3% quicker than the scan algorithm. This was probably due to it having to turn around much less with a higher capacity.
Hello, my name is Doruk, and I was responsible for making the MyLift algorithm in our lift system. The purpose of this algorithm is to be an improvement upon the look and scan algorithms that were previously made. And the way I wanted to approach this problem first was to use a priority queue so that we can actually find some sort of filter to decide which floor the lift should go to first and which passengers we should prioritize. So I used a priority queue, and I used a heap sort to, sort this priority queue so that we could tell the lift where to go and when to change directions based on efficiency and wait times of passengers and distance from the nearest passenger and everything like that. So the heap sort is basically an optimization over the selection sort. The way we use it is, first we make a max heap. So we imagine the array as a binary tree, and we look at the child nodes of every parent node, and then we swap them if the child node is bigger than the parent node. And this way we can get the binary tree all ordered, and in this case we have our priority queue all sorted. I have a couple factors here when I'm calculating the cost, and these being the wait times of passengers, and if there are multiple passengers on one floor, which would make it a better idea to go to that floor first because we're taking care of more passengers at one time. So the way we calculate the priority is we first calculate a base cost. This is the basic calculation of where is the passenger now, where is the lift now, and how much distance would the lift have to cover in order to get to that passenger and take them to their destination. This is the very start of our calculation and it gives us kind of like an indication as to how much this is going to cost us based on wait times and group bonuses. So then we use the waiting penalty on the costs. We have our iteration count, which symbolizes the wait times of the passengers effectively. So we multiply the current iteration count by the waiting penalty, which gives us another factor to use in our costs. And finally, we apply the group bonus. So if there's multiple passengers, that's obviously good. We're going to prioritize that, and there we have our cost. And we have an array, which is a two-dimensional array, and every element is the passenger and the cost of the passenger. So after we calculate the cost of each passenger, we're adding these to the new array that we've created, which we then send to the heap sort algorithm, and the heap sort algorithm sorts it based on the priority. So we have our queue here, and now we need to actually apply this queue to the lift and tell the lift to go wherever based on the queue. So we take the first element in the queue and we tell the lift to change the direction to wherever that floor may be. We have a different algorithm to find direction. So we find the direction and we start going in that direction. We take the passenger or passengers from that floor and we open the doors at that floor basically. And what the open doors function does is, if there is passengers to be picked up and the capacity is not at max capacity, then they will be let into the lift. And if there are passengers waiting to leave at that floor, then they will be able to leave there. So it's a subroutine that makes it much more efficient for us to manage the lift. And we've gone to that floor and we've done whatever we need to do with the passengers at that specific floor. And in that case, we can run the queue again to recalculate the cost of a passenger to their target floors, because obviously we moved the lift and time has passed, so wait times have increased for certain passengers. The cost of picking up passengers based on distance have definitely increased or decreased based on where we're going. Every time we reach a target, let's say, we need to rerun the priority calculation and the heap sort so that we can efficiently decide where we want to go.
This is a quick demo on how to use the program. So once you have downloaded and extracted the zip, you want to go into the main folder, and you then want to run the run.bat file. This should give you a command prompt window that looks like this. From this menu, you can choose what you want to do. You can either run a specific test file, generate a test file, or test all algorithms over a range of tests and view the graphs. Let's generate a test file. It then asks me how many floors there are. For this example, I'm going to say 12. How many people can the lift carry? Let's say 5. And how many people will there be? Let's say 100. It then asks you where you want to save this JSON file. So I'm going to navigate to the folder I was in before, and I'm going to save this as test1. It then brings me back to the main menu. Let's run that test file that we just created. When you select option A, it asks you to select a JSON file to run. So we're going to click on the one that we just created. It then asks you which algorithm you would like to run. For this example, we'll use look. It then runs the test file that you supplied it and shows you the results. So we can see that the total journey time was 1,410 fake seconds. The average journey time, so that's from when the passenger boards the lift to when they get off, was 48.08, and the longest journey was 124. You also see that in real time, it ran in 0.00038 seconds, which is very, very quick. Now let's say we want to compare all of these algorithms to each other. So we're going to select option C, and then it asks us if we want to generate all of the test files or test the algorithms. Because we haven't generated the test files yet, we will need to run option B. It then gives you a warning that a lot of test files will be created in the sources/tests folder. It also warns that it may take a long time, but we're sure that we want to continue, so we're going to hit Y. It then begins generating all of the required test files so that we can easily compare these algorithms together. Once it's done, we can hit C once again. And now we hit A to test all the algorithms. We then choose what variable we want to change, either capacity, floor count, or passenger count. For this example, we're going to select floor count. It then tells you the default values and asks you if you want to start. Once it's started, it'll begin testing each individual file with each algorithm. Once it has completed, it'll then show you the graphs that it has generated from the data. From here, you can use Matplotlib's standard built-in functions to zoom in anywhere you want on the graph and analyze as much as you want. The program also saves an SVG file of the graph in results and then charts. This is the one that we have just created. The raw data can also be found under results, data, and then under floor count.